Welcome to Programming in Modern C++. We are in week 9 and we are going to discuss module 44. In the last module, we introduced the standard library overview of C++, and most importantly, we have learned the fundamentals of generic programming, how to do meta programming in C++, which will be the backbone for the standard template library. So, in this module, we will understand the standard template library better and specifically take a look at some common container or data structures and their use. So, this will be the outline and will be available on the left panel. So, first let me formally introduce STL, standard template library, and it is customary to call it the STL. You will soon realize why. So, STL is a part of ISO C++ standard library. STL as such has 4 components: containers, iterators, algorithms. We have talked about these 3, and functions, which are basically function objects. So, these are the primary components of STL, but we do not say that STL is such a well defined subset, because we will see the use of these components in turn in almost every other component of the C++ standard library. Now, the STL is mostly non-numerical. There are only 4 standard algorithms that compute. These are the 4 standard algorithms. There is a component called numeric which does that. It can handle textual as well as numeric data. For example, it can most of STL can work with, say, things like string or user defined data type, right. So, it works with built in data type, user defined types, data structures, and so on and so forth. This amazing piece of the library is an outcome of about 15 years of research by this great computer scientist Alex Stefanov, who offered it to the standards committee and was subsequently adopted in very well in C++ to make things most generic, most efficient, and most flexible. Now, your question would be that is the ISO standardized STL or C++ standard library, is it the only one that exists in the world? The answer is of course no. There are several other implementations of the similar ideas of standard template library. The most common being Boost, which is a open source free peer reviewed portable C++ source library. The big advantage of Boost is Boost does a lot of experiments for the future generations of C++. Many of the things that we currently have in C++ standard library has evolved, or even the language features have evolved from experiments in Boost. So, you can consider contributing to Boost as well. There are several others which are commercial, like Microsoft Visual C++ STL, then others and so on, right. But most widely, the best known and most widely used example of generic programming happens in the ISO standardized standard template library only. That is the reason we call it the STL. It is not a STL, it is the STL that it is. We have talked about the basic model, that the basic model is to separate the concerns of an algorithm and the container separately. The container and algorithm interact through the concept of iterators, which go over the data structure in a physically or virtually linearized form to give the algorithm the next data element as and when it needs, and starts from the beginning, goes up to the end, or wherever you ask it to start and wherever you ask it to end. So, with that, the basic advantage we noted is that the iterators which are marked by the beginning of a data structure to one beyond the last element of the data structure can be clubbed with the algorithm, so that the algorithms do not need to know about the containers when those algorithms are coded. Right? They can just rely on the 3 operators of the iterators, which is plus plus to go to the next element, star to get the value of the element, and equality or inequality operator to check if 2 iterator values are same or not. In the same way, the containers also in turn do not need to know the algorithms that are applying on them. Their whole purpose is to support, every container must support the corresponding iterators, which are those 3 functions. Right. So, how do you conceptualize this on the particular container? If it is a vector, it is an array, it is a sequence container, things happen in a linear manner. So, the 0th location is the beginning, and one beyond the last location is the end of the iterator. It is not necessary that it will have to be that, it could be somewhere in the middle also. You could say I will start doing things from 2, I have done something else before that, and so on. For a list, this will again be the same. So, only thing that will get different is the way these 3 overloaded operators of plus plus, star and equality comparison are implemented by the respective data structure, which is the responsibility of the data structure, responsibility of the container to implement. So that algorithms can always assume that whatever data container they have, for that the corresponding conceptually same operations are available through syntactically identical code. And this applies, this concept of iteration applies also to nonlinear data structure, like a set which is in a binary search tree form. You can do an in order traversal of the tree to get the order in which the data elements will be given for the iteration, or your implementation could choose some other order. But all that you need is there has to be a unique starting point, there has to be a unique end point beyond the last element, and there has to be a unique order created out of this nonlinear structure. Now, with that we saw a find algorithm, which is very interesting in that it takes an iterator class in and the element type class in the template. So, then the find function takes 2 iterators, one where to begin, other where to end, defining the range, and the value as a constant reference, because you are finding. So, you do not want to change that value. Then the code is extremely simple, which you write in terms of first part checks that there are more elements to check, because first is not equal to last, and the second part checks if the current value star first is the value that you are looking for. If it is not, then you go to the next element, as simple as that. It is just an iterative find algorithm. No smart things like binary search or anything being attempted right now. Now, with this, if you have different types of containers with different underlying data types, but all of them support the iterator in the same way, the entire code that you write to do the find is exactly identical, because the algorithm find knew the iterator. So, algorithm find does not assume the data structure. The containers, whether it is a vector or a list or a double, has implemented the iterator, did not need to know whether you will find or sort or sum or do whatever, right. So, it fits in. You can see that except for the blue part, everything else in the code is actually identical, and this finally returns the iterator value. So, you have to check whether the iterator value is same at the end. If it is same as the end, that means you have crossed the entire data structure and you did not find the value. So, it is a failure. If it is not same as the end, again check the operator that the iterator has to support. If it is not at the end, then you must have got the value at the iteration point, which is basically the value star p, because p is your iterator here. So, this is how the generic algorithms are written. You will find this find algorithm in the algorithm component of the STL. You can even generalize this further, saying that instead of giving a value, I will give a functor here, I will give a predicate here, I will give a a function pointer or a function object which will check certain property. Right. So, I am saying that you go over this vector and find the first odd element. Right. Now, this oddness is not a value, oddness is a property. Right. So, I can write a function as a function pointer to check if a given value is odd, or I can write a function object to do that. I can pass either of them. So, what I am passing is I am passing an instance of the pred class, which is basically a function object. Right. So, I pass that. So, what happens is when I am trying to do the iteration over this data structure, I am just evaluating this function object pred with the given element. So, which is basically either a call to this function operator if I pass the functor as we have done here, or it is a call to this function if I have passed odd, if I just passed odd as a function pointer. Right. So, either of that can be used, and so this will make things even more generic things can be done. So, you can write any logic as a part of this function object, and you can find elements which can satisfy variety of different conditions. One catch point to note here is in the earlier form of find you needed to pass set the type of the element. Here you are not doing that, because you have set the type for the functor object. You have set the type for the functor object. So, this functor object here takes the element type. So, since you are calling odd for checking the checking as a predicate, it has to take an int. So, it will operate on the int. Right. So, that is the kind of deduction that the compiler would be able to do. Now, if you look into these two forms of find, you will find that the basic algorithm is the same. Start at the beginning, keep on checking on the value, keep on going till the end. Now, the way you check, that has been changed. In the case of find, the check was by equality. In the case of find if, it is by some other predicate. Right? It could have been equality also. So, such elements in the design of STL is called a policy. That is, generically speaking, I am trying to do find, and I have a policy for deciding how I find or what I find. Here is another example on this, which is from your more common domain of sorting. So, I have a record which has say two fields, one is of type string, another is of type character array, which is basically C style string. Right. One keeps the name, another keeps the address of a person. Right. Now, I have a vector for this record. So, I have of that. So, how do I sort? To sort, I need to, we have seen sort earlier also, but now look at it from the generic programming point of view. To sort, what I need to know? I need to know the range, where to start, where to end. So, where to start is the begin iterator, where to end is the end iterator. And what else you need to know? You need to know how to compare elements. So, that you pass as a function object, as a functor. Right? So, I have a functor implemented here as compare by name, which overloads the function call operator for a pair of record references and does a comparison by using the compare function of the string type, because these are strings. Whereas, I also have another functor for comparing addresses, which overloads the function call operator again for a pair of records, because to compare I need two records, but it does the comparison using strncmp function of the string.h header of C, because address is a C style string, long terminated array of characters. Right. So, you can see that basically if you look at sort, there is no difference in the sort, only thing that changes is the comparison policy. And based on that, the same sort code can be made to use not only on arbitrary data structures, but also on arbitrary policies. Right? So, that makes it really powerful, and this is what is known as policy parameterization. So, many of the algorithms available in STL has the policy parameterization. Often they have a default policy, but there is a provision to parameterize the policy as you want. There are some more compact ways of doing that as well. I have just shown as example here, but we will come back to this heavily when we do C++11. Here what I am using is I am using the concept of a anonymous function, a function object which does not have a name. So, the entire code is written here, and all of that struct, bool, operator, parent, all that are shortened in the form of a pair of square brackets, which is called a lambda or a closure object in C++11. We will see more of that. So, I can also write the policies in this form. Certainly, the advantage is that if the policy is simple as it is here, then writing it right inside the sort call makes it easier to understand, makes it easier to follow as to what exactly are you doing. Of course, if it is a big code, you will not be doing this, you will not be using lambda, you will be using a named object as we did earlier, but lambdas are available for doing this. We will see more of that. Do not worry about not understanding lambda, you will have ample time to understand lambda in the subsequent module. So, policy parameterization in general can be done through named objects as we have done, or through lambda expressions, depending on whether you want to reuse the same policy in multiple places, you will use a named object, or if you need to have a lot of comments therein, or it is quite a complicated logic and so on. Otherwise, just use a lambda. Okay. So, with that let us take a look at the common standard library components. So, this is just a very small part of the standard library, C++ standard library, but also it is a fact that possibly these components will cover 80%, 90% of your common usage. IO stream, F stream we have already done. Then there are a number of containers, of which also string we have seen in multiple places, we more or less understand. Vector we have seen in multiple places, but vector, map, list, these we will briefly discuss in this module to give you a better idea of the uniformity that exists between the containers of C++ standard library. Then there are other components which are very useful, the algorithms which give you all sorts of common algorithms, the numeric and the functional, and we will have more components come in when we do C++11 from the next week onwards. So, let us look at what is the structure of a vector declaration. This is not the complete vector class in the standard template library, but this is the representative part. So, the philosophy is, since there are multiple containers, the philosophy is to have as much of uniformity as possible. So, a number of containers have a number of functionality which is common, particularly you will have element type, right. You cannot have a container where you do not have element type, right, it is not possible. You will need iterators to write code in the model that we have shown. So, there has to be iterators. If we have iterators, there has to be begin and end of the iterator, right. Since it is a container, there should be some way to insert, some way to remove element and so on, right. So, these are standardized to the extent possible in terms of syntax, semantics, even name, right. So, that you do not really need to memorize a lot of things. If you understand it for one data structure, you will be able to guess most of the member functions and types of another container almost with 90% certainty, rest of it you look up the manual. So, all that we need is let me just explain vector, then we will go quickly over the rest. So, you need the actual underlying container, which is kind of T is the element type. So, elements is a pointed to T. So, it is an array, as you can understand. So, vector has a type definition, type alias for value type. So, if I do vector colon colon value type, I will be able to know what is the element type. So, that is defined as T. Right. So, that is a very easy way of doing things. So, at any point you can know this, and this is uniform for most of the containers. You need to use a iterator. So, you are saying using iterator. Now, what is the type of that iterator? I did not try to write this, because this is highly implementation dependent. This is not standardized, because this needs lot of optimization based on the particular machine on which the compiler will target. So, this is implementation defined feature. So, you do not need to really bother about what that whole type expression is. All that you need to know is it has a name iterator. So, you are working with a vector, your iterator type will be vector colon colon iterator. The nice thing about the uniformity is, if you are working with list, your iterator type is list colon colon iterator. If you are working with a map, it is map colon colon iterator, and so on. Then your iterator could be a constant iterator, that is, it does not allow you to make changes in the code, in the container. Values cannot be changed. So, you have a const iterator, which is also uniform, and then you have the standard member function. You have a begin. For the non const iterator, you have a begin with, for the const iterator, naturally with the const iterator it has to be a constant member function, and similarly you have a insert, which takes an iterator and a value and returns you an iterator, that is, you are inserting into the vector. So, you give the iterator to a point where you want to insert. So, it will be inserted before that, and that iterator will be returned. Similarly, you do erase by giving an iterator and getting back the iterator after the erase. Right. So, you can see that the whole target is to do a very uniform design, and as we will come to in the next data container type, you will see that how similar the entire design is. But before that, let me just quickly take you through some of the differences in semantics that may give rise to this. Syntactically, they are very similar. So, let us say I am talking about insert of vector. So, this is a vector that I have, and so this obviously is my iterator type P as a vector of integer. So, vector int colon colon iterator P. So, begin is here, right. I am starting at this point, right. Now, then, so P, I am sorry, let me mark it separately. So, P v dot begin will take me here, which is P, right. Now, I do 3 plus P's, 1 plus plus 1 plus plus 1 plus plus. 3 times I increment the iterator, which means P will now point to this element 3, clear. I define another iterator Q, same as P. So, Q will point here, but I do plus plus Q. So, Q points to the next element, right. So, this is how, given this code, I come to this iterator positions. Now, I do an insert with P of a value 99. As I do the insert, what will happen? It will get inserted before the value that P is pointing to, that is the semantics, and all values to the right will have to be shifted. So, all values will get shifted. So, P will get returned, whatever is returned is assigned to P. So, that is the position of the new element, right, you get 99. But as all elements get shifted, Q now points to 3, it was pointing to 4. So, Q actually has become invalid, it is pointing to something which is wrong. So, remember, if you insert in a vector, your pointers, your iterators, other iterators will get invalid. Similar thing you can see in terms of erase, the value immediately that have been inserted here. I am erasing that. So, as I erase, it will get removed, values from right will be pushed back, it points to 3, but q which was pointing to 3 will now point to 4, again it will get invalid. So, for insert delete in a vector, the side effect is that other pointers or other iterators will become invalid. Right. Now, see if I have a vector, what are the different ways I can traverse it? Obviously, there could be multiple that we have already seen. One is I can just use the index, very simple. I can use the index using a variable which is of type int. It is okay, but not very advisable, because the implementer may have implemented the index using some other type, say unsigned int. So, what vector does, in fact almost all containers do that, is they have a type variable called size type, which gives you the type of the size variables in for that container, right. So, it is better if you are using index, it is better to use size type, or better still I could have used an iterator simply. I am doing the same thing, just traversing it, right. So, I could have used any one of this. Of that, the iterator form is what we will slowly move more towards, because in both of these the actual code is closely bound to the fact that it is a vector, right. I cannot have kind of I cannot have do plus plus I and go to the next element in the list, right. So, I would prefer to go by the iterator's style. There are other with this iterator style, there are other styles which will be coming in C++11, particularly when you are doing a entire data structure traversal. For example, you can say the value type is x, value type we have already explained, and just colon v, in which case what it will do, it will start from the very beginning of the container and go up to the end. This is called a range kind of support. You can even simplify it even further by just saying it is auto ampersand. What auto ampersand means we will come to, right, in C++11, but just to give you a glimpse that iterator style is really strong, and you can see in here there is no date container, no type, nothing is mentioned. It is just the variable given, which is a vector of int in our case, but in given any other variable corresponding to any other container of any other underlying type, this will also work. So, let us consider a doubly linked list just to see the parallel. This is the node structure, which is trivial. T is the value, there are 2 links for the double link. Naturally, you have a link pointer as the header, right. This time it is the header, right. Now, you have the same value type, because that is the underlying type. The iterator and constant iterator types will be available. So, will be the begin for non-constant and constant iterator, end for non-constant and constant iterator, insert in the same way, erase in the same way. You can see exactly, except for this link star and the name list, everything else is same between this and the vector, because conceptually they are all same, right. So, the code is generic and can be worked in a generic way. Of course, depending on the difference of the semantics of the iterator, the side effects will be different. The same situation we are showing here, where we have the same data in the list with p pointing here and q pointing here, and I do insert of 99. 99 comes in, but since it is a list, there is no movement of elements. Therefore, q does not become invalid, which was becoming invalid for the case of vector, right. So, that is for insert, there is a case of erase also worked out. For the case of list, the insert and erase do not invalidate the other iterators, but for vector they do. So, there are semantic differences that you will have to understand, but generically the code and the structure are all same, and you can understand that on what context you should use a vector. Obviously, if there is no other reason you should use a vector, it is most efficient. You can grow both vector and list. Vector can grow only at the back, list can go at both ends. You can do insert, delete. Naturally, vector has more compact storage, contiguous, list have separate allocations. Let us look at the next container, which is very, very interesting, which is called a map. It is basically a kind of a, it's not it does not do hashing, but it serves a similar purpose. In a vector, you use an integer as a subscript. In a map, you can use anything as a subscript. Almost any type you can use, type of value you can use as a subscript. After vector, map is probably the most useful standard library container to be used. It is implemented as an ordered balanced binary tree. So, let us look at the basic structure. I have the value type. So, map is a name value pair. So, I say this is PPD and this is his age, this pair always. So, the left one is called the key by which you index, and the right one is the value that you. So, the value type for a map or the underlying types, element type for a map is a pair, a key type and the value type, and you pair them. Pair also is available in the STL to take a pair of types and make it into a pair type, which becomes the value type for the map. But you have the value type anyway, you have the iterator, constant iterator, begin, end, all this. Additionally, in map what you have a way to access an element. Actually, you have this in vector also, you do not have it in list because list is not indexed. You have a way to find, because in map finding is somewhat different. Your insert works differently, because now you are not inserting based on the iterator, you insert based on a value, right, and you get basically the key value pair, whereas erase works on the iterator itself. Let us just take a look at an example of a map. So, I am doing a map which is a char int pair. So, key will be char, value will be int. So, the pairs I am creating is A10, that is character A 10. So, you can see the standard array notation coming in here. I can just say my map, give that index value and assign the value. I can do this. There are other ways of doing that also. I can do this by insert. If I want to do this by insert, I have to make a pair of these two values. Say I am basically trying to do this. The key value is C, actual value is 30. So, I make a pair of them, I insert, right. So, these are different ways you can do insert add elements to a map. Then you can do the printing using the basic iterator style. Here you are getting the iterator, and since map has two components of the pair, the first is the key, second is the value which prints these values. You can do a find on map. To given a key, you can find what is the value that it has, right. So, this is very, very useful, and there is another example which is given here. I am not going through this. This is example of using a map to find the frequency of different words in a text. So, just try this out and convince yourself about the use of map. There are other containers also. Set is another which keeps this collection of unique elements. It is also stored as a binary search tree, And just wanted to show you the uniformity, the value type, iterator, const iterator, begin, end, insert, erase, just signatures a little bit here and there, very similar to what you have for map, but set is also a useful container. There are many more, but it is time to close on this module, and here we have learnt about the standard template library with common components. Particularly the focus has been on learning the basic containers, vector and map, and some of the others that will also come in, like string and set and so on, and what is their use. So, thank you very much for your attention, and we will meet in the next module.